Okay, welcome everyone. I will present you a piece of research that we do in my team. So I'm Ioana Manolescu. I'm a researcher at INRIA in France. And I'm going to present now a paper that our postdoc Madhulika has presented this year in ICDE. If some of you attended, then it's a repeat, but if you didn't, then hear it out from me. So the problem that we're looking at is flexible in querying of graphs. And by flexible, I mean finding connections that the users are unable to describe in any way. So the users are just able to say, I would like some things to be connected to others and possibly to other things, and I really don't know how. So here you have a sample graph where nodes have IDs, types, and some relationships, and we have labels on nodes and labels on edges. And the question that this user asks is, how are US entrepreneurs, French entrepreneurs, and French politicians related? So what you see here is that instead of asking for paths between, let's say, US and French entrepreneurs, this is a three-pronged query. Because or search, let's say, we have some information about what each of the nodes should be. So we would like some nodes to have a type entrepreneur and lives in France. That makes them a French entrepreneur. And other nodes similarly to satisfy other properties that are local node properties, and the users can say that much, perhaps, but we really do not know how they may be connected. So arbitrary connections between two or more groups of nodes, that's the problem that we're looking at. And a solution to such a problem is a tree. For instance, here you have a tree that connects Doug, Falcon, and Carol, each of which matches the respective conditions on the nodes that we want to connect. And you can see that in this tree, the edges converge towards org-C that happens to connect them all. But in general, we want to solve this problem regardless of the edge direction. So edges could have been in any direction, we would still treat that as a solution. Why is that? Because graphs can be complicated and users don't have to know in which direction the edges go, right? That's not something you can assume. So fundamentally, with respect to state of the art in the area, on one hand, you have query languages such as Sparkle and Cypher and also GQL that perfectly allow to search for nodes that have some properties or to spell out your path if you know how to spell it out, who have varying capabilities for searching for paths that you are not specifying precisely. So for instance, in Sparkle, you can check if a certain regular expression path exists between your variables x and y, but you need to specify a regular expression, so you cannot say give it any path, and you cannot get it to be returned to you. So you do not get the path, it's just a Boolean check. In GQL, as this certainly knows, there are beautiful primitives that allow you to get back the
I haven't looked at the bags for a while.
However, you have three groups of nodes. Okay.
Two more expensive reports to do.
That is Keith, and I will have to open Zoom and mute him.
Okay.
Yeah.
Thank you. So we cannot. So in GQL, you cannot currently, at least to the best of my knowledge, since I heard that there is always progress on the language, you cannot specify I want connections between X and Y and Z at the same time. Of course, every smart person in this room will tell me, but I can always write three paths and stitch them together and have a tree. And I will show you that in principle it's possible, but in practice it doesn't work well. Okay, so that's what structured query languages do. Now, at the same time, there exists a literature on a problem that looks different at the first sight, but is quite related, which is called keyword search in databases, where we consider that the users specify keywords such as, Obama and Ukraine, and the database system must figure out how this could be related. And keyword search algorithms work regardless of the number of things that you want to connect. So they are a good source of inspiration somehow to come to our problem and say, how can we solve this? Now, what is annoying about the previous solutions here, on one hand, they are not really integrated in a query language, but that can be arranged more or less. But more fundamentally, each of the algorithms that has been published makes some simplifying assumptions. For instance, that some connections are better than others, and this quality function is injected into the search so that the algorithm would only develop some of the connections, only those that hopefully are the best or approximate answering where you're not sure it's the best, but this is what you get. You only get an approximation. So this,
May have to click back.
yes, it's okay, okay. So why do people do this? Why do they condition their solutions on a cost function or something else? Not because they're mean, but because the problem is NP-hard. So when you are given 3 groups of nodes in a graph and you ask, find me a tree that connects one of each, that problem is NP-hard in the size of the graph, which is like sit down and die immediately. Nothing can be done. And it's not only theoretically hard. I mean, this is one of the problems that really kicks you into the nose, really. It's really hard. That's why people propose approximate solutions. So why are we so crazy as to say we don't want any of that? Because we have users. So we work with journalists and we integrate very heterogeneous data sources into graphs. And you cannot tell them, you have a K-optimal solution, or we find you the shortest path. I played this in a graph that contains French National Assembly members. The shortest path on average between 2 people is the path that says that they are both male. That is true, but it is utterly uninteresting. So in some applications, nobody cares about the shortest path because the shortest path happened to be the shortest, but it is not the most interesting. So if you have the unfortune of dealing with users, they will say, I don't care about K-approximate or something that goes through a hub or whatever. I would like to know if this person paid money to that person, corrupted a politician or did something. And there's no computational assumption I can make about that. Okay, so what we want to do is to get a query language and enrich it with the functionality of finding connections between 2 or more sets of nodes that basically will become query variables. So we want to say you will write a query, you will have variables on nodes that specify whatever the language already allows you to do. Say that there must be politicians, they must be French, they must be young, whatever. And also allow you to connect such variables with a general algorithm that searches for trees, undirected in the sense that edges should be traversed regardless of the direction in which they are specified. Find all the answers under a space and time budget, because as I said, this is a real NP-hard, which means that in general, nobody is going to run it to the end in the most general incarnation. So it will stop at a timeout or when you have already a bunch of solutions or just before you run out of memory. And in a way that is independent of the cost function. So that was important, okay? So our algorithm, you can plug any cost function, but it's not going to use it to prune the search. Okay. And of course, we try to do this as efficient as possible, whereas the odds, as I said a few times, are not generous. So I'm not going to take your energy to recall what GPML supports. So we have path patterns and we have graph patterns that are conjunctions of path patterns. And what we propose is to invent a new thing that is called connecting tree pattern that is extremely simple syntactically. It's a kind of tuple of variables where the first 3 are node variables that come from another place in your query, or maybe also be free variables if you want, which means they are bound to any node in the graph. And the last one, which we underline for visibility, is a variable which will be bound to every tree that is an answer. So in every tuple of bindings X, Y, Z, W, if I show you an example here, so this is our query which says that we want these people to be entrepreneurs and politicians of such and such country. And we also want W, which is bound to every tree that connects a specific binding of X with a specific binding of Y and with a specific binding of Z. Okay, so what we return here is the trees. So W is a variable that is bound to a tree, which you can view as a set of edges. I think the least cognitive dissonance with the existing language design is to say that W is a set of edges, and the application may interpret it correctly as a tree. What you do with these results later. Good. So you know, binding XYZ, you're perfectly well known. And, you know, if you have this tuple of bindings, Bob, Alice, and Ellen, then that is one result that you get. Okay, the whole thing is a tree. Okay, so, and there are more results, of course, for different tuples. So how do we do this? We had previously published an algorithm last year, which is building the trees from the bottom up, which is a well-known historical way of looking for keyword connections, where we start by creating exploration trees of size 1, each of which comes from a binding of a variable. And then we basically grow around them. So we have two main steps, one that is called grow, which adds an edge, and one that is called merge, which merges two trees that have the same root. Okay, so we grow an edge and we merge, we grow an edge and we merge, and it's called GAM because of grow and aggressive merge, because it has been known since 2010 that these algorithms are optimal in a well-defined way if you merge as soon as you can. So aggressive merge is important. As soon as you find that coming from a French politician and from the American politician, you have the same root, you merge, because that will immediately make a bigger tree, and it's a good thing. Okay, now, the problem with this algorithm, so this algorithm is complete, and it returns answers that are correct, but the problem is that it builds what we call all possible rooted trees. So here you have a solution of 3 nodes, and our algorithm, being nice and exhaustive, is going to develop this tree rooted in each and every node that it has. So because I managed to sell you on the idea that we merge trees, that highlights the important role of the root of the intermediary trees. Trees can only merge at the root. So where your root is will differentiate two trees that span over exactly the same edges. Okay, and in turn, that makes a duplicate effort of search, because you're going to find this thing rooted in every one of its nodes. But for the user, it doesn't matter where the root is, because the root is just an algorithmic artifact. Okay, so you're wasting effort, and it is actually inefficient. So, yep, it's okay. So then we brought some optimizations with the main idea that what we wish to do is to only build for a given set of edges, only build one tree. So that's what we would like to do. So that would be, when we build a tree for this set of edges, the second one will be immediately discarded. You're not going to do it again. So that's nice, and it works for paths, but it doesn't work if you have an arity greater than 2. And you know, this example is a good thing to take home from the talk, is that in this example, we found a tree that connects Alice and Bob, and the root is here. And then we will allow no other tree over the same edges because of the pruning. And unfortunately, we found Alice and Falcon connected in the green tree with a root here, and no other tree will be built over these edges. And then we are stuck because these two trees, the green and the red, will never merge because they don't have the same root. You see? So the ESP pruning, edge set pruning that says I'm going to build only one tree over a given set of edges will make you lose solutions, because the roots that survive are kind of arbitrary, and you may not be able to merge partial solutions into complete solutions. Okay, so just ESP won't make it. Good. So then we brought a set of optimizations. One of them is to carefully inject a little bit more trees. So whenever we merge, if the merged tree has more keywords than both of its ingredients, if it covers more, which it always does, otherwise we don't merge. If we build more trees that are rooted in each of the seed nodes. So we basically inject a little bit more trees that will allow for more merge opportunities later. So this MOSP optimization will already save the day in this example. And it may still fail to find some specific results. And then we brought other optimizations that are based on introducing a signature for every node that determines how many of the starting points this node is connected to. And connected to is across the search history. So some nodes are favored because when we find that this is connected to Alice, If later another tree connects it to Bob, we're going to say, oh, that's a nice node. This is a nice route. Let it live because it is connected to more keywords. So we are basically pushing back on the ESP pruning so that we can get more completeness guarantees. And with this and a few more details that we have in the paper, we formally established that we are complete for trees of arity 3. And for trees of arity 4 or more, so if you're trying to connect 4 or more variables, let's say, depending on the execution order, you may miss solutions or you may get the solutions. Okay, so for more than 4 or more, it's a matter of luck because the algorithm that we have is not driven by any fixed order. So depending on the order in which you build the trees, knowing that the first one over a set of edges will still prune a bunch of others, you may make it or not. Okay, so details are in the paper, but what I want you to understand is that this is and remains an NP-hard problem for which we have competitive algorithms for the graphs that we tried, and it works much better than what is called path stitching. So what we call path stitching in the paper is saying, I'm not going to search for trees, but I'm going to search for as many paths as I need, and I'm going to put a common variable to stitch them together into a tree. That's the name. We tried several systems here, the state of the art. We tried Virtuoso, we tried some research prototypes, we tried Neo4j. Fundamentally, ours is better because if you know that you're looking for a tree, you should be building trees and not paths that will make you waste some effort. And that's fundamentally the message. We described it as an add-on to GPML, but you could see that the add-on is really minimal. It's just a small atom that can be used as conjunction with other standard GPML pattern atoms. And we are still working on things around this. And if you want to find out how we got into this, we have a project called Connection Lens where we're trying to integrate really, really wild data into graphs. And the graphs are really wild as a consequence for journalists because they have a bunch of heterogeneous data sources and it's very cool. And the code is up there. The code is Java based. You can give it a look and see the paper.
Excellent. We have time for one question. Wim.
I have a short one. In your experience, which arity do you need in practice?
I think that it may, 2 is the most frequent. 3 is also nice. 4, good. There could be applications, but I think that beyond 4 is really kind of, I don't find.
Can you repeat the question to the Zoom audience? Yeah,
so the question was what arities for this kind of thing are useful in practice? And my answer is that probably 2 and 3 are by far the most useful. What was important is to be able to return the paths, no matter what, and have direction independent search and not be limited to shortest path. Okay.
Right. Thank you very much.